people have heard of the planets in our solar system, and in fact, you probably have seen them with your own eyes. Jupiter and Saturn are easily observed, even under conditions which have not so great seeing and are perhaps not so dark. However, there is more to just the planets in the solar system. There are also this kind of rubble pile that seems to have built up between Mars and Jupiter, and there's this streaking thing across the sky. These are known as solar system small bodies. Small because they're small, and bodies because they're bodies within the solar system. Yet they're very important to understanding the initial composition of the solar system and its dynamical history. This talk will briefly introduce what we know about solar system small bodies before exploring interstellar objects, which we think are the small bodies from other planetary systems around completely different stars. Okay, so let's take some time to appreciate some nice pictures of comets, asteroids. We can actually send stuff to take up close photos. So let's start there. These objects initially are part of the solar system when it is born. And as they collide and interact with each other, they stick together and they are the building blocks of planets. So if we can understand these objects, we understand how planets are built. This is an artist's impression of something called a protoplanetary disk. So this is what the baby solar system may have looked like. Here is the sun, here is some planets, probably Jupiter, and it is collecting all of the material in its orbit, and it is growing bigger and bigger and bigger until it reaches its current state. Here's another artist's impression of a perhaps slightly even more evolved solar system. So here you have Jupiter again. It's now cleared out everything in its orbit. So it's clear space here. You have inner planets. So maybe that's Earth, maybe that's Venus. You got these streaky guys again. And you've got a lot of leftover rubble that unsuccessfully did not form a planet. Now, these are comets and these are asteroids. Asteroids are the stuff that's in between Mars and Jupiter for the most part. There's also some that are beyond Neptune in the Kuiper Belt. And comets are even further out and they're flung into the solar system. So let's go over where these things currently live. So the asteroid belt between Mars and Jupiter, they're roughly 2 to 3 times as far away from the sun as Earth is. Going further out, you have the Kuiper Belt, which is somewhere between 30 to 50 times as far from the sun, and it's out past Neptune. Finally, you have the very, very distant Oort cloud. These are comets that are orbiting the sun some 200 to 200,000 this Earth distances away from the sun. So they're out in the cold, dark interstellar space. For reference, some of you may remember the Voyager probe. The Voyager probe has not left the Oort cloud yet. Okay, so back, comets, asteroids, these two kind of families of small rocks in the solar system. There's a clever mnemonic that astronomers use to remember the difference. If you can't remember anything else, comets are dirty snowballs. So they're mostly ices and they have a lot of dust in them. So dirty snowballs. And asteroids are snowy dirt balls. So they're mostly just dirt. But they're exciting space dirt, and they tell us about the origin of the solar system. And we've been observing these small bodies for quite some time. This is the Bayeux Tapestry. It documents the Norman conquest of England some 1,000 years ago. And they took the time to etch in, or to stitch in, Halley's Comet. 1,000 years ago, people were observing Halley's Comet and going, man, what the heck is this? Fast forward a little later, 1618, the artistic style has changed. But again, you have a comet streaking through the sky, and people have been fascinated. They thought it was so interesting, they documented it. It's not Halley's Comet. This is the Great Comet of 1618. But still, 400 years ago, people were observing comets and going, man, that's cool. Here's Halley's Comet again. Same comet, 900 years after the Bayeux Tapestry. This was observed by the Yerkes Observatory in Wisconsin. And this picture, it's slightly more detailed than the previous picture, so we can maybe go over a little bit of cometary anatomy. So these will be some terms that I might use throughout this talk. So this streaky part, this is called the tail. And this right here is the cometary head, which is centered around the cometary nucleus, which is kind of that dirty snowball in the center of the comet. And what's happening is the sun is a deadly laser in space. If you've ever gotten a sunburn, it's not pleasant. Comets are suffering from sunburn. And they are sublimating all of that dirty snowball material off behind them. So the sun hits it, it evaporates, and you get this tail of material coming from the comet that's being pushed by the sun. Okay, one more really pretty picture from 1986, the last time Halley's Comet came around, and this was taken on Easter Island. So lots of exciting, very, very photogenic. Comets love the camera. They love the attention. They're very beautiful. Asteroids are more like what Willem complained about, just dots in the blackness of space. This is an asteroid observed by JWST right next to a really bright star. Asteroid, really bright star. And they move across the sky with respect to the stars. So this is another kind of interesting tidbit about objects in the solar system that makes them different than objects outside of the solar system. On the sky, the stars appear as fixed points, and they kind of just rotate around the Earth. Objects in the solar system move in relationship to these fixed points on the sky. So here's an asteroid. Generally, to observe these, you're not going to get as many with naked eye, and they're not going to show any spectacular features. Although I will highlight that there was one well-observed great asteroid some 65 million years ago that the dinosaurs had the pleasure of seeing. Unfortunately, that was the only one they got to see, which kind of brings us to another one of our key antagonists in this story of Three-Eye Atlas, the discoverer. So in preparation for this, actually, before I talk about that, I have one other highlight, one other public service announcement, and that is Apophis, which is, I think, the Egyptian god of chaos. It's a near-Earth object, so it's, again, one of these pieces of rock in space, and it is going to approach the Earth extremely closely, to the point that when it was initially discovered, there was over a 1% chance of it hitting the Earth. And you might say, oh, 1% chance. I'll take my chances. But in that 1% chance case, that's not a pleasant experience. Just ask the dinosaurs. So here's an animation showing Apophis coming by its closest approach on Friday, April the 13th. Maybe you want to rethink that 1% chance. And again, very close to the moon. So there was a lot of concern that something like this would hit the Earth. There's a little bit of concern that it would hit the moon too, but I personally think that would be really cool. But yeah, stuff like this exists in the solar system, and it might hit the Earth. And so we want to see this sort of thing before it hits the Earth so we can get our cameras ready. And that brings us to Atlas. I've shamelessly stolen this slide from Larry Deneau, who's in the back. And this denotes these red circles, denote a network of telescopes all around the world, including 2 in Hawaii. So Atlas is based out of Hawaii. Its first facilities were in Hawaii. And their job is to find rocks in space, these asteroids that could hit the Earth, and let us know ahead of time so we could potentially do something about it and prepare. Atlas has this bonus of discovering all sorts of exciting other stuff. Supernovae, tidal disruption events, the things I researched for my dissertation, and Three-Eye, it's in the name, Atlas. Here's the discovery image. And if you're thinking, man, I can't see anything in here, you'd be right. And this is one of the challenges with the Three-Eyed Atlas discovery, and indeed observing things in the night sky in the solar system. You don't get to pick your brand new comet's location. You don't get to pick where your supernova gets to explode. So you have to fight through a lot of not ideal conditions, just in terms of where it's located. In this instance, Three-Eye Atlas was located in the Milky Way. So there are billions of stars in the Milky Way, and Three-Eye Atlas is hiding amongst them. It's like playing a game of peekaboo, but there's a billion different rooms you have to search. So inside this giant image, Three-Eye Atlas is in this red square. As helpful as this red square is maybe to highlight where Three-Eye Atlas is, even when I blow it up, it's a little difficult to see. So maybe let's blow this image up just a little bit more. Here is the discovery night from Three-Eye Atlas, right? Look at all of these stars. All of this, and Three-Eye Atlas is just hiding right there. One little dot in the darkness of space, surrounded by a bunch of other little dots. As I mentioned earlier, though, these sorts of objects move against the stars. So it is like playing a game of peekaboo in a billion rooms. But the nice thing is whatever you're looking for has to change rooms every so often. So the night that it was discovered, the way it was discovered is by tracing how it moves against the stars. And you can go, oh, something wasn't there last night. This is where I need to look. Okay. So as Willem mentioned, there were 3. This is the 3rd interstellar object. So this is a top-down view of the solar system. Here you have Jupiter, this green circle. It's really far from the sun. This red circle is Mars, because it's the red planet. Blue circle is Earth, because we have all the water. and the yellow circle is the sun, that giant deadly laser in the middle of our solar system.
Mr. Willem, are
Yes.
you taking questions?
Sure, we can do questions.
So you said that the first picture was the day of discovery or the night of discovery.
Yes.
But you need to have subsequent pictures after to show that they're moving.
Same night.
It was the same night.
Yes, the same night.
Okay.
Just because you've taken one picture doesn't mean you can't take another one until the next night.
I don't know these things.
No, you can take as many pictures as you want of any area of the sky. So yeah, that's actually one of Atlas's design features. It takes pictures of the same area of the sky 4 times each night, so that way you can see objects move across the sky throughout the night. And that's what makes it particularly adept at finding these sort of solar system or interstellar objects. Okay, so we've had 3 so far, and they're denoted in black. So I'll go through them one by one. First, we have One-Eye Oumuamua, which was discovered by Pan-STARRS, a somewhat similar survey to Atlas that is based on Haleakala. And it is this orbit. This is its orbit right here. The star is where it was located when it was discovered, and the circle is Earth at the time of discovery. So Oumuamua was discovered almost right when it was on top of us, and we didn't know it was there. And part of the reason we didn't know it was there is because it was very faint, it was very fast, and it was very difficult to observe. So here, more dots against the black emptiness of space. This is Oumuamua in some imaging, and these dots and lines are stars. So rather than following the motion of the stars across the sky, we follow the motion of Oumuamua across the sky. Just this little pinprick of light. Very difficult to find, very faint, especially when you compare it to the stars, right? Oumuamua is very, very hard to see. And it also didn't do what comets normally do. It didn't have a tail. It didn't sublimate any material. It was just this rock, very much like an asteroid. So again, analogous to something we've seen in the solar system, but tricky to observe. And the most fascinating thing about Oumuamua is that it had a very large aspect ratio. We thought it was very long and very narrow and very thin. And so that it raised a lot more questions than it answered, because this is something that, you could think, oh, okay, it exists. You probably can get these sort of things from other solar systems, maybe. Some crazy theorist probably thought of it and we've forgotten their name, unfortunately. But okay, it's more of a let's wait and see. How many more of these are we going to find? Are they really, really rare, or are they really, really common? And 2 years later, we got the first inkling of an answer, and that was 2I Borisov. So 2I, second interstellar, Borisov. Borisov is I'm going to say amateur. That just means he's not on the payroll of any astronomical institution. But a lot of astronomers, whether they are amateur or professional, can make serious contributions to astronomy. And I think that's one of the beauties of astronomy, is that anyone with a telescope or a camera can do astronomy. You don't need to be a professional. Okay, so Earth was a lot further away from Borisov when it was discovered, right? And maybe if you remember, so Oumuamua was over here. Oumuamua came in and went out. So Oumuamua was discovered on its way out. And really, we want to discover these objects on their way in, because as they approach the sun, they emit more light, they lift off more gas and dust and ice, and that tells us about their composition. And I'll talk about that later in this talk. For now, all that we need to know about Borisov is that it was a comet. It showed this tail, it showed this emission. This is a picture from the Hubble Space Telescope. So again, you can see the comet head, the comet nucleus right here, and then this tail material, right? It's all of that snowball getting evaporated away by the deadly laser that is the sun. Okay, that brings us to the discovery of 3I Atlas. So 3I Atlas was discovered on its way in, almost at the orbit of Jupiter, right? So really far away from the sun, really far away from the Earth. And we've been able to observe it from here. And actually, I think the date of the original talk, it was here. So we've got the whole, Jupiter to Jupiter. It spans one Jupiter between its discovery and this talk. So it's done a lot of moving. And so we've discovered something new and exciting. We've done that initial discovery image. We want to confirm the orbit, right? Because we want to know how it's going to move. When's our best chance to observe it? It got pretty close to Mars there, right? And here it's going to get pretty close to Jupiter. So we want to be able to refine this sort of orbit. So it should play again. Yeah, perfect. So again, close to Mars. Here's where it gets closest to Venus, closest to Earth. and now closest to Jupiter. So it moves right along through the solar system. Okay. So we follow it up. Here are some images from the Canada, France, Hawaii telescope, also on Mauna Kea. And you see 3i Atlas here. It's kind of this smudge, small pinprick of light against the darkness of space. And you see, like Oumuamua before, right? We're following the movement of the comet as opposed to the movement of the stars. So the stars are trailed. And then once you average out the images, you can get rid of the stars, those pesky stars, and you're just left with the nice comet, right? So center and a little bit of fuzz. And this is the image right after it was discovered. It's far away from the sun, and as it gets closer to the sun, it'll get bigger and brighter in terms of apparent size and how bright it is. Okay, so we've got this really exciting discovery, the third ever interstellar comet. What is an astronomer supposed to do? You're supposed to fly to Rome, go to the steps of the Senate, and make a speech. Friends, Romans, countrymen, lend me your telescopes. And that is what we did, although we unfortunately could not pitch it into a trip to Rome. That night, we were observing on the University of Hawaii's 88-inch or 2.2-meter telescope on Mauna Kea as part of the SCAT team, which is the spectroscopic classification of astrophysical transients, which I suppose 3i Atlas is. It comes in once, it's transient, it's only here for a short time, and it will leave the solar system to be gone and never come back again. Although maybe one day we will get a return visitor. So we were on the telescope that night, and I got some cryptic Google chat from my PhD supervisor, Ben Shappy. He's like, Larry has something. Larry's got a ton of stuff. What does this even mean? Like, question mark, question mark, question mark, question mark. Turns out, new interstellar objects. Can we observe it tonight? And the answer was yes. And I'll talk about some of our observations from Hawaii facilities a bit later in this talk. But NASA also got the memo. And I don't think they were able to pitch it into a trip to Rome either. So, Mauna Kea, what telescopes did we use to observe it? Sure. Keck, yes. Trivia time. Does anyone know this telescope?
Subaru.
No. It's okay. This is the University of Hawaii 88-inch. This is the Gemini telescope. So this is 8 meters. Right here is Canada, France, Hawaii telescope. So you've seen images from Canada, France, Hawaii. You've seen the tidal site with UH-88. And then for complete list, this box is Subaru.
Oh.
I knew it was blocked.
Subaru's got a very distinctive dome. So if you were ever at some trivia night and they go, which telescope on Mauna Kea has a box as a dome? Subaru. Okay. As I mentioned, NASA got the memo too. NASA has a big portfolio of spacecraft and missions. So this is the Mars Reconnaissance Orbiter. It is a satellite that is orbiting Mars. It is supposed to point and take pictures of Mars. What did NASA do with the Mars Reconnaissance Orbiter? They took a picture of 3i Atlas. They were able to turn the spacecraft around, which is at Mars. They were able to communicate it. They were able to say, hey, point here. 3i Atlas is going to be here. And right, you can't just communicate with something with Mars. You don't just FaceTime with something in Mars, right? There is a lag between when you send the message to Mars and when it gets to Mars. So you need to predict in advance where 3i Atlas is going to be. So we were able to figure out where this object is going to be in advance. We were able to move this telescope out of its design's mission operations, right? It's not meant to look at space. It's meant to look at Mars. And it was able to take this photo of 3i Atlas. So even though it looks like a grainy iPhone picture, it's incredible because we put something in orbit around Mars and we used it to take a picture of something that came from a completely different solar system. Okay, what else can we do with NASA's missions? This is Parker Solar Probe. It is the closest man-made object to the sun. It goes through the solar wind, so the sun emits a ton of particles, and Parker Solar Probe just collects information about that particle. It helps us answer things about the sun. Can Parker Solar Probe observe 3i Atlas? Well, I've set up the punchline. The answer is yes. Again, pinprick in the darkness of space. But here you can see 3i Atlas moving in Parker Solar Probe data. So again, this is a probe meant to collect particles around the sun and also take pictures of it that took pictures of 3i Atlas. And I'll highlight that these observations are actually quite useful. You might think, oh, they're kind of blurry, they're kind of grainy. Why don't you use something better? 3i Atlas was unobservable from Earth when these images were taken. So this is otherwise inaccessible data from Earth. So we were able to use these facilities beyond their intended use, which I think is super cool. All right, the show goes on. NASA, Punch. This is another solar studying mission. It observed 3i Atlas as well. Is this a movie? Yeah, this is a movie. So again, 3i atlas. It's supposed to look at the sun. Okay. You can also use traditional astronomical facilities in a slightly a-traditional way. So this is NASA's TESS mission. So this is the space telescope. It's designed for nighttime astronomy, even though it's in space. Its goal is to discover transiting exoplanets. So a lot of astronomers at the IFA use data from this mission to discover exoplanets. You can also observe 3i atlas with this mission. And here's a nice image of it moving. Again, this probably illustrates it pretty well. Like, here are the stars, and then here's 3i atlas moving against the stars. All right. I actually want to take a pause because this image also illustrates something very interesting that I was talking with Lark a bit before this talk. And Lark asked, what was the hardest thing about 3i atlas? Like, what was the most challenging thing? And I was actually observing it. Because it was in the Milky Way, there were so many stars that, let's run this animation again. So there's so many stars in the Milky Way, right? Like when 3i atlas goes over a star, some stars are faint, they're not very bright. So 3i atlas is mostly unaffected by the star. But sometimes, like this star up here, it goes across a very bright star, and you're just stuck with starlight, and the data you took is not very useful. Now, if you're trying to observe it for just a few seconds, okay, it's pretty easy to find your spot and take a clear picture. But if you're trying to obtain some of the data that we'll be talking about later in this talk, you need to observe for 30 minutes or an hour. And so if you have a star go through your observation, it's like a satellite going through a traditional astronomical data image, right? It ruins your data because your signal gets swamped out with this thing you don't want. So that was one of the challenges of observing 3i atlas when it was first discovered. Eventually, it moved away from the Milky Way and became a lot easier to observe. But that initial few months were very technically challenging to get data. Okay, Hubble Space Telescope produces these beautiful images. And one of the questions you can answer with Hubble Space Telescope is how big is it? So we'll get to that in a bit. And then finally, NASA's most recent shiny toy, James Webb Space Telescope. It can get us information from wavelengths that we can't observe on the ground. And this helps us answer a question such as, what is 3i atlas made of? Okay, so let's start getting into kind of what have we learned about 3i atlas? First, how big is it? So I mentioned that we can do this for Hubble Space Telescope, and we could do it. We have Hubble Space Telescope images for 2i Borisov and 3i atlas. And to answer, how big is it? A couple kilometers. So it's not as big as the meteor or the asteroid that hit when the dinosaurs got the chance to observe an asteroid. But it's still big enough that you probably wouldn't want this to land in your backyard, as exciting as that would be. In comparison to what we see from the solar system comets, we see a wide range of comet sizes in the solar system. This one is, I think, the biggest ever discovered. It's just ridiculously large. It's almost 85 miles long. 3i atlas and 2i Borisov occupy the smaller end of things, which makes sense. It's much easier to form and eject smaller bodies from a solar system. Nature tends to prefer small things. Okay, so that answers how big is it? About a mile. What about how old is it? So this is a picture done from some dynamical modeling, and this is the Milky Way galaxy, or an artist's impression of the Milky Way galaxy. So the Milky Way has this bulge of very old stars and this disk of also very old stars. And if you trace the dynamics of 3i atlas from where it came, dynamically, it suggests that it should be very, very old. So this is interesting because it tells us about something about the universe, about planets, potentially older than the solar system. So I'll also touch this back a little bit later when we talk about spectroscopy, because spectroscopy provides an independent measurement of 3i atlas's age that is in agreement with this dynamical picture as well. Okay, let's talk about a plot. This is going to be very information dense, so we're going to go through it very slowly. But I think this is the most exciting thing that interstellar comets do. And they tell us about the composition of exoplanet systems. They tell us what the planet-forming material around other stars looks like. Directly. We don't have to infer. We don't have to assume. We have planet-forming material from another solar system in our backyard to study. And this is one of the ways that we do it. So this plot shows distance from the central star, and I'll unpack that a bit in reference to the solar system. And the vertical axis shows you the ratio of carbon to oxygen. And that is a tracer of the location in that protoplanetary disk that this small body formed. Okay, so let's revisit the radius. So right here, you have Earth. This is how far the Earth is from the sun. Earth is on the very far edge of this plot, and we're not as interested in it. What we're interested in are the giant planets: Jupiter, Saturn, Uranus, and Neptune. And we're interested in understanding different cutoff points for these lines. So this blue shading, what does this blue shading? It's where H2O, water, undergoes a transition from being gas to being solid. So anything interior to this line cannot form as a planetesimal with water because the water is in gas phase. Anything beyond this line should have lots of water because water is a solid at that phase. So let's look at this. Think Jupiter, Saturn, Earth. Earth shouldn't have formed with any water. So this is kind of an interesting question in astrobiology, is where does Earth's water come from? And one of the hypotheses is that it's delivered by small bodies that form out here, and then these giant planets send them inward to deliver water on Earth. So that's interesting. So if you're thinking about exoplanetary habitability, you probably want to be able to form comets out here, and you probably want to be able to send them interior to the solar system to deliver water to your Earth-like exoplanet. So that's something really cool to think about as well. And we can play this game now. This C to O ratio game requires a few other ingredients. And the next ingredient on the list is CO2, carbon dioxide. Same argument as water. Anything inside of this purple shaded region can have CO2, should have a lot of CO2, because CO2 can be a solid out here, solid, gas. And so any of the objects that form in this range should be very CO2 poor. And then finally, our last ingredient is carbon monoxide. It's got a very large range of gas phase, right? Anything inside, 20 times the distance from the Earth, that'll be gas. But anything outside of that, all the way out to infinity, will have lots of CO. Okay, so what do we see in the solar system, and what do we see from 3I Atlas? Okay, solar system objects. This is where they generally form. So Oort cloud objects don't actually form out in the Oort cloud. And I'll talk about that a bit later. They form somewhere around here in between Jupiter and Earth. And then the Jupiter family comets, or Kuiper Belt objects, form roughly around Neptune, and they're much closer to their formation than Earth. What happens to the Oort cloud objects is that in the early dynamical history of the solar system, Jupiter and Saturn started in a nice alignment. They ended up in a 2-to-1 resonance, which caused a lot of the objects in the Kuiper Belt and where objects around Jupiter and Saturn to scatter, either outward or inward. So this scattering took this belt of objects and either sent a bunch of water into the Earth, or so we think, and it also sent a bunch of objects out to the Oort cloud, where they were retained by maybe gravitational influences from a nearby star, or potentially tidal forces from the Milky Way itself. Or they were completely ejected or lost to interstellar space. So this could mean some aliens halfway across the galaxy are also losing their mind about 10I Earth because something came from the solar system and passed through their own system. So our solar system also produced a lot of interstellar objects. So it is not a finders keepers world. Okay, so what do solar system comets look like in their composition? Well, I mentioned earlier that they formed in different spaces, so we expect to see slightly different composition, right? Carbon-enriched comets form, these are the Jupiter family comets. So they form outside of that water line, outside of the carbon line, and they have lots of carbon. Carbon-depleted comets, those are your Oort cloud comets, right? They've formed interior to those CO and CO2 lines, so they have lots of water, because water was the only thing that could be solid at that phase. So that's a tracer, right, of where they've formed. We see this in the solar system. Okay, what about the weirdos in the solar system? We do have weirdos in the solar system. So this is one of the more peculiar solar system comets we've had. CA 2016 R2, some phone number, but it was mostly carbon monoxide and carbon dioxide. not a lot of water. So that's a bit of a head scratcher, but okay. Most solar system comets show these typical compositions. Why is this one so special? Well, it turns out that 2I Borisov and 3I Atlas are a lot like this solar system weirdo and not like the typical solar system comet. So for example, 2I Borisov had a lot more carbon monoxide than the typical solar system comet, right? Just eyeballing this, maybe we can say this is like 2/5, and this is, a tiny sliver. This is like 3/4, right? So its composition was dominated by CO. 3I Atlas is even more perplexing because its composition is dominated by CO2. So this tells us, okay, maybe 3I Atlas formed in some sweet spot where it can get a lot of CO2. And so if we put these objects on that previous plot I showed before, this suggests that they formed far away from their host stars. Somewhere nice and cold, somewhere where they can get these CO and this CO2 into their composition. So again, we can't identify which planetary system these objects came from exactly, but we know it had to be cold and they had to have formed far out in their protoplanetary disk. And there's one other implication to that. And the other implication to that is that if you think about the solar system comets, right, they needed to be ejected by Jupiter, or often it's Neptune. Jupiter and Neptune are kind of the big bullies in the solar system. They're the ones that eject a lot of material. What this tells us is that in their host systems, there needed to be some sort of giant planet out at this very far away distance, the distance of that we don't have any major bodies in our own solar system. There needed to be something at that distance that ejected them. So that's interesting. And as we build a sample of interstellar objects that probe these planetary formation conditions in other solar systems, that'll tell us maybe about the distribution of planets that eject interstellar objects by tracing their compositions. Okay, let's move on. We're going to show another plot, but to
Floyd, Dark Side of the Moon.
exactly. Bonus points for Mark up front.
You tell I'm a rock fan.
You can tell he's a front row student. All right. White light comes in. Pink Floyd, Dark Side of the Moon. White light comes in, it hits the prism, and the prism splits the light into its different wavelengths. It splits it into different colors. This is a technique called spectroscopy, and astronomers use it every day. The instructor that teaches the astrotechniques course flippantly jokes, if you're not doing spectroscopy, you're not doing science. The jury is still out if that's true, especially considering he does a lot of imaging. But okay, what does that actually look like in practice? What happens when you split the light up into its different wavelengths or different colors? It gives you something like this, a squiggly line on a plot. Let's walk through it. On the bottom axis, we have blue light to the left. So this light is much bluer. And as you go to the right, this light becomes much redder. So it's called wavelength because light is a wave. So it has a characteristic length. And this is the little unit of wavelengths called angstrom. So it's 1 × 10⁻⁻10 meters, which might not be particularly helpful, but if you're looking for a baseline, the human eye starts to kind of kick in right around here-ish. So it's a little off the plot. So a little bit of what you can see, but mostly what you can't see with your own eye. Okay. And then the vertical part tells you how much light there is in that given wavelength. So you can think of it as a proxy for brightness, right? So right here, there's not a lot of light, it's kind of faint, but then right here, blam, there's tons of light. And so this light, the source of this light can tell us about the comet. And in fact, it tells us what the comet is made of. So different molecules and different atoms emit different wavelengths of light. So when you excite them and they emit light, they do so at characteristic wavelengths that we can know, and then we can study. So 3I Atlas emitted all of these different features. Very interesting, very exciting. But which one's the most interesting and most exciting? In my opinion, it's these two all the way at the end, right? Between 3,400 to 3,800 angstroms, something called the ultraviolet. We can't see this with our eyes, but we can measure that with our telescopes. And the interesting thing is it's not some molecule. It's not carbon. It's not oxygen. It's nickel. It's iron. Why is there nickel and iron in a dirty snowball? If you're throwing dirty snowballs with nickel and iron, you might get kicked out of recess because that's a bit mean. And this is actually kind of a big point of confusion for astronomers because we only recently identified ubiquitous nickel and iron in solar system comets in 2021. So we've been observing comets for thousands of years, and we just now realized, oh, there's more nickel and iron in them than we think. So what can we do with that? We can calculate how much there is in a comet. And then we can use that to compute. We can ask questions of like, how much nickel is a lot of nickel compared to other comets? And so here's another plot. On the bottom, we have far from the sun on the left. This is far away from the sun now. And closer to the sun is on the right. So this is a distance away from the sun. Comets are very sensitive to this. As they get closer to the sun, they emit more material. So you would expect that your light gets brighter. And if the amount of light corresponds to the amount of atoms you have, you would expect more atoms as you get closer. Okay. And then vertically, we have not that much nickel and a lot of nickel at the top of the plot. And I mentioned that we only just discovered that solar system comets have a decent amount of nickel in 2021. And this is what the solar system comets look like. There's a decent spread, but interestingly, there's not a particularly strong trend with distance from the sun. So that's a bit interesting. So that means maybe that trend needs to happen further away from the sun. Maybe it means there's no trend at all from where this nickel comes from. And we don't know where it comes from. It cannot just be nickel on the surface of the comet because nickel likes to be a solid at room temperature. And even at hot temperatures, nickel likes to be solid. So you're not going to evaporate nickel off the surface of the comet. It needs to be coming from some molecule that then breaks apart from light from the sun. But we don't know what that molecule is. We don't know the nature of that molecule. No idea. Okay, so that's what the solar system comets do. What do the interstellar comets do? 2I Borisov kind of fits in with this, but we only have a couple of measurements. So, okay, 2I Borisov is mostly consistent with this nickel picture. 3I Atlas is just completely different than anything we have observed so far in terms of its nickel, and then also I mentioned iron in terms of its iron. So this paper was before we observed a lot of iron emission. So it's only doing nickel, but 3I Atlas does two things. One, it has way more nickel than any other solar system comet, right? Like look at the solar system comets. 3I Atlas is way up here. So it's got a ton of nickel compared to anything else from the solar system. And unlike these solar system comets, which don't really show much of a trend, 3I Atlas is incredibly sensitive to as it approaches the sun, you start seeing way more nickel. And one of the questions is this just because we've observed 3I Atlas so much better than we observe typical solar system comets? Again, we've observed solar system comets for thousands of years. It's hard to get excited when you discover a new one. You kind of roll your eyes, you click, Atlas found another one, and you go back to bed. You don't call all your friends going, I got something awesome. It's just another comet. But maybe we need to rethink that picture, especially in light of this mysterious nickel. The other thing I want to highlight is we can look at the evolution of the ratio of nickel to iron. So this is, again, I'm going backwards and forwards on you, I apologize. So this is distance from the sun, same thing, but now this is close to the sun on the left-hand side. So close to the sun, and this is far away from the sun. And then this vertical axis is a ratio of how much nickel to iron you have. So things that are high up on this plot have a lot more nickel than they have iron. And on the opposite side of things that are down here have way more way more iron than they have nickel. I've plotted already, no dramatic hype, solar system comets and 2I Borisov. So the solar system comets, a lot of them are piled up here. They were observed when they were either close to the sun or close to Earth, so they pile up right on here. And you can see there's just a spread. Some of them are a little more nickel rich, some of them are a little more nickel poor. They're just kind of this clump. 2I Borisov was observed a little further away from the sun. And it also seems to just kind of be consistent with this population of solar system comet. And there's a couple of solar system comets out here, including that really peculiarly composed one from earlier. So that's the only other comet that has this sort of measurement, 2 to 3 times as far away from the sun as the Earth does. And if we look at 3I Atlas, 3I Atlas is, again, very perplexing. It shows this very strong trend with distance from the sun. And this isn't something we've observed in other comets, but we don't really have the data to really say, oh, we don't actually observe it from other comets. It's more of a, we can't really say for solar system comets. And then the interesting thing is it starts out very nickel rich. It continues to produce a lot of nickel, right? That previous plot showed as it got closer, the amount of nickel went up strongly. But what is interesting for this to evolve like this, it means the amount of iron that it has goes up even more strongly than the amount of nickel it has. And so this point right here, one little point, this is another astronomer's work, and I got this point. You may think, oh man, he only got 1 point, he's really owning it. Let me tell you, that point was a challenge. We were observing on the Keck telescope. So that's a 10-meter telescope on the summit of Mauna Kea. 3i Atlas had just passed the sun. So it was very difficult to observe, and you couldn't observe it because most of the time it was during the day. And that's not where astronomers like to observe. That's where we like to sleep. So, okay, we're on the Keck telescope. It's coming up, it's sunset. We have a 10-minute window where we can observe 3i Atlas before, one, it gets too close to the moon. Two, after it gets out from behind the Keck 1 dome, so there are 2 telescopes right next to each other, and the dome for the 1 telescope was getting in the way of our observation because it was so low in the sky. And then 3, the sun's coming up, and so we have a limited window from the sun coming up. We started moving the telescope ever so slightly early, and the telescope operator had to leave their chair, go into the dome, and reset a lever to let the telescope override its failsafe once it was safe and obtain that point. That is the closest spectrum in the optical to the sun of 3i Atlas, and that was the one I showed you earlier. So this trend with nickel and iron, shown with the post-perihelion observation, confirming it, is really interesting, and it's something that 3i Atlas has brought about solar system comets. So maybe we need to spend more time thinking about this, because both Borisov and 3i showed this emission feature. We don't know where it comes from, but it seems to be very ubiquitous in both comets from other planet systems and from the solar system. Spitballing a little bit, let's look at this chart. This chart is the origin of the solar system elements. So the different colors correspond to different sources, and then the different elements are just elements on the periodic table. Our antagonists for tonight mostly come from exploding massive stars and exploding white dwarf stars. So this is supernovae. This is my bread and butter. This is what I love to think about every day. And then here are nickel and iron right here. Nickel, iron. And you can see that nickel and iron, the amount that they have depends a little bit on how much exploding white dwarf you have and how much exploding massive star you have. So maybe, and this is very hypothetical and no one's really looked into this because we haven't had a lot of time to think about it, can we tell the supernova enrichment history of interstellar comets using these nickel to iron lines? And that's kind of an interesting question that I'm starting to think about a bit more using both my supernova expertise and my comet experience. Okay, so spectroscopy, same page. I mentioned we can also use spectroscopy to age 3i Atlas. How do we do that? This is a picture I took. I was down in Chile doing some observing. I also went to a museum. And this is an Incan relief. And we want to age this Incan relief. How do we do aging? You might have heard about carbon dating, right? And that's the idea that when something dies, so say if this Incan relief was found next to this, the burial site of this figure depicted in it, how old is this figure? How do we know? Well, when a living thing dies, it stops absorbing radioactive carbon and that carbon decays. And you can calculate how old it was based on the ratio of carbon features. That same process, comparing 2 different lines to see how old something is, also can work in astronomy, both with radioactive materials and also just other isotopes. So we can age date 3i Atlas by looking at its composition. And a couple of papers that came out maybe a month and a half ago did just this. So here are their results. So we can walk through the plot. The horizontal axis is just bookkeeping. So don't worry about the horizontal axis. And we'll start with this plot up here, the blue one. This is the ratio of deuterium to hydrogen. So deuterium is a special kind of hydrogen. It's called heavy hydrogen. And the reason it's called heavy hydrogen is much more massive because instead of just being a proton and an electron, it also has a neutron. So because it has slightly different atomic properties, its spectrum looks slightly different than hydrogen's when you add it in place of hydrogen. So if you observe very finely, you split your light up into very small colors, you can tease out how much deuterium and how much hydrogen an object has, and that is a proxy astrophysically for age. And if we look where 3i Atlas is, it's up here in the shaded region. Solar system values are down here. Comets are down here. So what's this telling us? It's telling us that 3i Atlas is significantly older than the solar system. Okay, the same exercise works over here as well. So we can do this with deuterium to hydrogen. We can also do this to carbon-12 to carbon-13. So the difference again is one neutron that changes your spectrum, that changes the light that it emits ever so slightly. And if you make a very precise measurement, you can see the difference in the spectrum. You can measure the amount of light from each different carbon. And you can see again, 3I Atlas is much older than things in the solar system. And you can repeat this exercise using different ways to measure deuterium, and you can repeat this exercise using nitrogen as well. And the recurring theme is, both dynamically and using spectroscopic tagging, that 3I Atlas is from a planetary system that is maybe twice as old as the solar system. So this is telling us something about the planet formation, not only of other planetary systems, but of planetary systems that are twice as old as our own, maybe planetary big brothers to the solar system. So that's really exciting for interstellar comets. And that's an avenue, right? When we get more interstellar comets, we can make more of these measurements and we can build a sample. We can build an in situ understanding of interstellar objects and exoplanetary systems. Okay, I'll just end this talk with some future directions. What does the future hold for interstellar objects? And it's this facility right here. This is called the Vera C. Rubin Observatory. And it has been long anticipated by astronomers. But why? Here's one reason why. This is the amount of new discoveries in the solar system LSST is expected to make. LSST starts. Within a quarter of a year, it's already discovered 1 million new solar system objects. That's 1 million more comets and asteroids to study. I love this animation, so we're gonna watch the whole thing. It's just mind-boggling. Like, look at how much it's discovering. There's 3 million dirty snowballs and snowy dirt balls out in the solar system that we have not discovered, that LSST or the Vera C. Rubin is going to discover.
You're gonna be busy.
Hmm?
You're gonna be busy.
Yeah, I might have to stay awake during the day. So it's slowing down after the first couple of years. It's got all the low-hanging fruit. But it's still, after 5 years, or after 3.5 years, it's still discovering many new things each night. So that's exciting. We're going to discover a lot more solar system objects. And maybe you're asking, how many interstellar objects is it going to discover, right? Those are the exciting ones. Don't tell me about solar system objects. It's very difficult to answer that question accurately. It depends a lot on the assumptions you make about the nature of interstellar objects. But we can say maybe somewhere between 6 and 60. So more than a handful. So thank you, everyone. And hopefully there are more interstellar objects in our future.
I don't understand. You had the ratio of nickel to iron changing. Why? I mean, it's one body. So how does the ratio change?
Yeah, that's a good question. We don't know what the nickel and iron is bound to. So it's got to be some molecule. And this molecule that binds the nickel might break apart more easily than the molecule that's bound with the iron. So as you get closer and closer to the sun, you catch more light from the sun. So you get blasted by even more radiation from the sun. And so you can break apart these tougher bonds. And so the reason why the ratio changes so much is because you're breaking apart that tougher bond. And then as you get closer, you can break it apart more and more and more and more and more. And so does that make sense why it evolves? And we don't know the nature of this molecule, if it is even a molecule. So that's kind of an exciting new question.
Following up on that one, is there any effect of volatility as a function of temperature in space? Roger.
Yeah, that's the.
I mean, there's obviously a greater energy flux when you get closer to the sun.
Yeah.
And iron and nickel don't have the same volatilities.
Yeah, that's it. But we know it can't be nickel and iron because they're not volatile enough to be just by themselves lifted off, right? So there are, for example, asteroids and meteorites that are mostly nickel and iron in their composition. If you've heard anything about like space mining, people want to send like rocket ships out to these, collect all the nickel and iron, or like, send it back to Earth because it's like, if you could take one of these things, it's, thousands of kilograms of nickel and iron. Like, oh, hey, I got thousands of kilograms of nickel and iron for sale. So we know that, you won't break them apart just by dousing it in solar radiation. So it needs to be linked to a molecule. So yeah, it's exactly that. It's differences in the volatility of the molecules.
I mean, in a microenvironment at the planet's surface, the solar energy that you're getting in all its various forms or wavelengths has got to cause microheating at an environment, which will be related, will have some relation to bond energies,
Yeah.
right?
That's exactly it.
That would be, and I'm sure,
But we
I
don't.
don't know what those compounds are either. So.
Yeah. Yeah. So we have some ideas. You can bond them to carbon monoxide. So they're called carbonyls. And we think maybe it's that, but there's a couple things about that. Like the evolution doesn't quite line up with what we expect the bonds of carbonyls to be. The other kind of challenging thing for the carbonyl picture, if that is the molecule, is that on Earth in the lab, so big asterisk, because these are not forming on Earth and they're not forming in a lab, but on Earth in a lab, you need somewhat high temperatures to form these molecules, to push them into the configuration they need to form. But 3I Atlas, right, formed far out from its disk. It formed somewhere cold and old. So that's somewhat inconsistent with being able to form a carbonyl. So there are still some challenges. Yeah.
So my question, so looking at the distance from this, away from the sun and the amount of nickel or iron, has anybody looked at then another axis of size of the body that it is? Would that affect how much of these are coming off? Because in theory, if it's a larger body, then it would hold on to it more. Does that make sense in space? I don't space.
So these objects are pretty small. Their names are small bodies. So their gravity is basically negligible, right? That's why they lose the material in the first places. Gravitationally, they're pretty wimpy. Size might matter. If you have more size, you have more area. So you could lift off more particles. I don't know if anyone's actually made measurements to compare size to nickel and iron. The size measurement is actually very difficult. You need something like Hubble Space Telescope to make a size measurement.
Like, I guess like in my head, yeah, not spacing. Like it would be interesting to like standardize so that they're all in like the same size, and then how much nickel and iron are coming off if they were all the same size.
Yeah, I agree.
Does that kind of make sense?
If you could take a gram of every.
Yes.
I agree. In theory, that would be amazing. In practice, it's very tricky. These observations are really tricky. There's only a few instruments in the world that can really do this. This whole nickel and iron thing. And then on top of it, to do sizes, you have to go to space because comets have all of this fuzz around them, right? So how big is the comet actually? Well, if you just measure the light, that doesn't tell you how big it is actually, because the light is from all the fuzz around it. So to get through the fuzz is challenging, and it's a very tricky thing to do. So there was one, yeah, go for it.
With the Oumuamua and Atlas, they didn't seem to have too much tails. Isn't that like a characteristic of a comet? And I think Oumuamua didn't even have a tail. So is it actually classified as a comet?
Yeah, so Oumuamua didn't have a tail at all. That's correct. There's a little bit of back and forth about is it a comet or is it not, because we saw a lot of non-gravitational acceleration, and that's generally something that's attributed to comets. So, but no tail. 3I Atlas definitely has a tail. I just didn't show any pictures with a tail. I apologize. But if we go all the way back to the title slide, it's definitely a comet because it's got a lot of fuzz around it. So this is so many slides. Goodness, this guy. All right. So I made this image and I purposely scaled it so that it would kind of look fuzzy here. But if you zoom out and take other images, with a giant tail across. I promise you it has a tail. I just didn't show it. I'm sorry.
You know when that Oumuamua happened, wasn't there kind of a thing where they even questioned as to, because it was long and it didn't have a tail, that it might have actually been a probe or something from somewhere else that had
Yeah.
people on it? I mean, it's kind of far-fetched, but I remember it came out and there
Yeah,
were people that
yeah.
actually were behind that theory, but they couldn't tell.
Yeah. So I will say that the people
I mean,
every one of these that's come along, there have been people who've claimed it's aliens or alien probes. I think,
no, but that one was in particular because it didn't.
Yeah, sure.
anything.
But I'll say,
Personally, I didn't believe it.
yeah, I'll say for that one and for all of these ones, if you look at like the typical things you would expect from an alien probe, radio signatures,
Right.
orbital movements from thrusters or something like that, and all the predictions that certain groups make just never come true.
Yeah.
The evidence is pretty weak. And then just from a psychological standpoint, I was thinking about this the other day. I was like, man, it'd be so cool to send a probe to another solar system. Like that's totally something we should do. But if you think about it, I kind of want to do it because I want to see what's happening. But in my lifetime, there's no way we're going to get a probe to another solar system. So why would any alien want to send a probe that it's never going to see the data from? I find that hard to believe.
Didn't another thing that's happening this year, I think, is Voyager 1 is making one light day.
I'm not sure about that.
You know how,
Yeah.
because but
Yeah.
I mean, it's slow, but on that time scale of the universe. But in all the 50 years it's been traveling, it's only made one light day.
Yeah, exactly.
But that's how big it is, and that's how far away it is.
Yeah, and it's not even close to another. It hasn't
No,
even
yeah.
it hasn't even left the Oort cloud.
Nothing.
So again,
Yeah.
why would any aliens send space probes that are going that slow, right? If these interstellar objects are not
Just
coming
how
in.
long something like that would take, even if they had a lot more speed to get to another, like the comets that we see. They've been
Yeah.
traveling for a while.
I think
Yeah.
I don't know if we would detect something that would be moving fast enough to get to another solar system,
Yeah.
right? It would just come through and it would just
Yeah.
so. Other questions? Yeah.
Yeah, is 3i Atlas, is it the oldest of the three? Or we were not able to kind of date the other two using techniques that are available today?
Yeah. I don't think we have a good age estimate on Oumuamua, not like from spectroscopic techniques. I would have to double check the dynamical age estimates to know for sure. But 3i Atlas is definitely very, very old. I think the estimates on Borisov are younger, and I think Oumuamua is too challenging to estimate.
Super interesting talk. I was just kind of wondering about how interstellar objects are even kind of identified in the first place. Are there like mathematical models? Like how do you know what section of space?
Yeah, that's a great question as well. So everything that is in the solar system is bound to the sun. So it's orbiting either as, say, a circle or an ellipse, right? So if we look, so many slides. Okay, so if we look at this plot, where's my stick? Watch my stick. So if we look at this plot, right? Earth goes around the sun. Good. We should be very thankful for that. We wouldn't last long in interstellar space, right? Jupiter is also going around the sun. These interstellar objects come in, and when you compute their orbits, there's something that is known as hyperbolic, which means instead of coming around again and again and again and being bound, they come in and then they go out and they're unbound. So you just compute the orbit, you solve, it's basically an equation that you solve. And if it's hyperbolic, aka there's an eccentricity. So if you think about ellipses, how eccentric, it's a Thursday. If you think about how eccentric an orbit is, right, these are eccentricities much, much greater than 1. So 3i Atlas had an eccentricity measured of about 6. So when you measure that and it's greater than 1, that tells you it's very likely an interstellar object.
How long does it take to calculate that? How much of the movement do you have to see to extrapolate the orbit?
To do it quickly, you just need like the 4 points that Atlas will get in a single night. To do it well, it's much more complicated. But to be able to say, is it interstellar, is it not interstellar? You can just use like those 4 initial atlas points. Those are usually sufficient. But then you can look back from previous nights and go, oh, I see it now again in previous nights. And you can very quickly build up a large set of data very quickly.
What's the derivation